Hi everyone, welcome to a video on basically stats 2018, the A2 paper, question 5. I'm going through all the normal distribution questions basically in the next half an hour from the most recent stats papers. They're often some of the trickiest parts of the paper, not all of it, but I mean the last sort of like part can often be quite a difficult part of the question. You've got a lot in that normal distribution chapter, everything from like approximations of the binomial distribution, hypothesis testing, finding mean and standard deviation or both, so you might have to standardize. There's lots and lots of ideas in that chapter. Anyway, let's get on with it. So this is question 5 from 2018. We've got batteries. Now, I remember kids came out of this, my students came out of this exam and said the normal distribution question was so hard, and I think they're right. It is a difficult question. So let's have a look. Straight away when I see that, I think I'm going to write down L squiggle N. It's got a mean of 18. Oh, let's write it a bit neater than that so you can read it. And the standard deviation is 4, so put 4 squared there because we just always write variance here. It's just what we do. Now that's just of one battery. Now we're looking at 4 batteries. That immediately makes this question more awkward, doesn't it? So Alice's calculator requires 4 batteries and will stop working when any one battery reaches the end of its lifetime. So all of them need to be, need to have some, some juice in them. Okay, find the probability that a randomly selected battery will last for longer than 16 hours. So this is just a randomly selected battery. This isn't all 4, this is just one. So the probability that one of these lasts longer than 16 hours, well, this is one where we can just use our calculator. I'm doing this all live, so I'm going to do all the calculations on my calculator. Normal distribution, this will be normal CD, not normal PD. You'll never use normal PD in your A level. I can promise you that, because it's something very different to normal CD, where you're actually finding the area underneath the curve. It's generating the y coordinate on the normal distribution, if you're wondering what normal PD does, and why would you ever need that? So, wait till you get to university before you need that. So I'm going to go for a lower bound of like a very negative number and an upper bound of 16. Oh, sorry, no. It's longer than 16 hours. Yeah, L is greater than 16. So I'm going to go for a lower bound of 16 and an upper bound of like 1,000. Sigma is 4 and mu is 18. It doesn't help that your calculator, you enter these values in a different way, and I'm getting 0.69 146. Yeah. Now you've got to round this to 3 sig fig, haven't you? So let's just call it 0.691. Okay, there we go. Okay, so that is the first question. Now part A, and that's worth 1 mark, so there's 1 mark for you, and that should be easy. At the start of the exams, Alice puts 4 new batteries in her calculator. She has used her calculator for 16 hours already, but has another 4 hours of exams to sit. Okay, right. So find the probability that her calculator will not stop working for Alice's remaining exams. Well, we need all the batteries to work. So let's find the probability that 1 works if you've got another 4 hours of exams to sit. So firstly, find the probability that they last for 20 hours, given that they've already lasted for 16. That's a really subtle bit, isn't it? You need a conditional statement here because you know it's already lasted for 16, so that's been given to you. Find the probability that they last for another 4. Find the probability that L is greater than 20, given that L is greater than 16. Now, with normal distribution conditionals, you can use the formula. The formula does work. We need the probability that L is greater than 20 and L is greater than 16, divided by the probability of what you're given, which is that L is greater than 16. But if you look at that top statement, if I told you something had lasted for longer than 16 hours and it had lasted for longer than 20 hours, surely I'm really telling you only one thing there, and saying it's lasted for more than 16 hours is redundant. And so that's just L is greater than 20. Yeah, and that's why your normal distribution conditional probability will always work like that, because you've just shrunken the sample space. You are no longer worried about 16 or greater. Well, you already know that you're only dealing with this area, and so you find the area of 20, if I can colour it in a bit thicker, and then just divide it by the probability that L is greater than 16, because you've just shrunk the sample space. That's all it is. Okay, so we're going to work out those two values. We've got the bottom one already. It's 0.691. We haven't even dealt with the fact that there's 4 batteries yet, so we're just going to work out the probability. This is the probability that one of the batteries lasts, any one battery lasts for 20 hours, given that they've already lasted for 16. So that's what I'm going to work out. So I'm just going to do 20 as my lower this time, Okay, I'm getting 0.3085 on the top. Yeah, and it's only the final answer I need to put to 3 sig fig, but even then this isn't the final answer. So let's now come out of normal distribution and go to 0.3085 divided by 0.691. And I really worry about rounding errors in these kind of questions. That gives you 0.446. And if you use the full calculator displays, you should get 0.044621, I believe, yeah? If you used this one carrying on going, and that's why it's worth actually, keeping the 4.6 on the bottom there, because it will change things slightly. Now, that's just the probability that one battery lasts for another 4 hours, given that it's already lasted for 16. We need all 4 of them to do this, so we need to do... This is essentially a sneaky binomial now. I would describe it as a sneaky binomial. The probability that one battery lasts, that you have success with one battery, is that. But you need it with all 4. So we're looking for the probability that x equals 4. That's essentially what we're doing. But most students, I think, will be just comfortable saying this needs to happen 4 times on the trot. And so I'm just going to do this to the power of 4. And that comes to, let me quickly work it out on my calculator, 0.0396 to 3 sig fig. Yeah? Cool. Okay, now when I first did this question, I was like, wow, that's come up in part B already. That's normally the end of the question, something as difficult as that. I knew that they were onto a real hiding in this question. It's a nasty question. Okay, let's do the next one. Alice only has 2 new batteries. So after the first 16 hours of exam, although her calculator is still working, she randomly selects 2 batteries from her calculator and replaces these with 2 new batteries. Show that the probability that her calculator will not stop working and for the remainder of her exams is 0.199 to 3 sig fig. Wow, so we've got to really think about this. Okay, so what is the probability that out of the 2 that she selects, what is the probability that she selects 2, like the 2 that she leaves are going to be still working? Well, what we need to think about this very carefully. Let's have a little look. The 2 new batteries are going to be pretty much fine, yeah? Although I suppose you should really do the calculation. We need, with the 2 new batteries, now let's just write down what we had initially. I'm just going to write down the original distribution, 18 and 4 squared. L, 18 and 4 squared. Yeah? Well, each battery, let's just say that you're taking the batteries which are new first, yeah? Let's just consider the new batteries. What have the new batteries got to do? Well, they've just got to last for 4 hours. Now, you would have thought that was practically guaranteed. You'd be let down if, on average, they last for 18 hours, and you just trust that, and you suddenly find out they didn't even last 4. That would be really, really shocking. But still, we need to work out the probability that they last for another 4 hours, yeah? So that's the 2 new batteries. We need them to last for 4 hours, yeah? Now, that's just one battery, yeah? The probability that it lasts for 4 hours. We need that for the first new battery, and we need the second one to do that, yeah? Now let's think of the other batteries which have been in there, which we know have already had 16 hours and need to last for another 4. Well, with those, we need the previous answer, because we've already worked that out. Well, not the final previous answer, but, let's not move that. That's messed everything up. This value here is the probability that any one of the old batteries lasts another 3 hours. So if I just star that and say, well, I need that, yeah? I need that for the 2 old batteries, yeah? So if I can call these the old batteries. So here I'm looking for 0.44621, because that's the probability that any one of the old batteries lasts for another 4 hours, yeah? And I need to square that. So that's what I'm actually going to do here, yeah? Can you see that? That's the, because that's the probability that for any one of the old batteries, they last another 4 hours, because it's probably that they last longer than 20, given that they last longer than 16. And so we get this set up. It's a very difficult question. Now, if you work that out, probability that L is greater than 4 under those conditions. It's easy to type into your calculator. You obviously get a very high probability, because you would expect it. It actually comes to 0.99976 if you do that on your calculator, but we need that to happen twice, so I'm going to square it, then I'm going to times it by this squared, and I'm going to get the final answer, which is 0.199, as they said it would be. Yeah. Now, what I was wondering is if you just take if you ignore the new batteries, I wondered what they would give you. I'm going to have a quick look in the notes in a second. Let me have a quick look. What would they give you if you didn't bother with the new batteries and just thought, well, they're going to be fine and just squared this? It might be an M1, MB. Oh, yeah. No, you score nothing. You score nothing for that. That is really harsh because, I could completely understand why you might think, the new batteries will be fine. But because this squared on its own actually comes to 0.199 to 3 sig fig, I'd say it's a really poorly written question that for that reason, like that you can't. It's for the markers. The markers must have been spitting feathers about this, because if you miss that probability that is greater than 4 and just squared, just looked at the two old batteries, you receive nothing. I think you should get a 1 out of 3 for that. Anyway, right. What we got last? We got the hypothesis test. Now note the hypothesis test will not rely on any of the conditional stuff you've already worked out. It really won't. It's unlikely to anyway. Now what have we got? After exams, Alice believed that the lifetime of batteries was more than 18 hours. She took a random sample of the 20 batteries and found that their mean lifetime was 19.2 hours. Stating your hypotheses clearly, test this at the 5% level of significance. Okay, so it's a one-tailed test, because she believes that it lasts more than 18 hours, and we've got a sample of 20. Now, never forget, when you're doing a hypothesis test, well, let's write it down like this. X squiggle n. Now, the mean was 18, and the standard deviation was 4 squared. But don't forget, when you're dealing with a sample, and you'll do this in every hypothesis test with a normal, you need to take you can look at this in two ways. You either take the variance and just divide it by the sample size, but personally I would note, because you need standard deviation on your calculator, that you need to take the standard deviation and divide it by the square root of the sample size. That's just to account for the fact, if you like, and this is a very crude and elementary way of putting it, but there will be less variance in the sample, if you like, almost every time. And so we're dividing it by 20, and so we're reducing the size, we're dividing the standard deviation by the square root of 20, so we're reducing the size of the variance, because in a sample you're never going to get as much variety as in the population. That's a gross simplification of what's really going on, but it's normally convincing enough for students to remember you must change the standard deviation in any normal distribution hypothesis test. It's really important that. Okay, right, what do we do next? Well, she took a random sample of 20 and found their mean lifetime was 19.2. So we're going to find the probability that X bar is greater than or equal to 19.2. Oh, and I haven't even written down my hypotheses yet. Let me write down my hypotheses. I like to write those down early because they're easy marks. H0 is that the mean is still 18, but H1 is that the mean has increased and is greater than 18. Now this will not be greater than or equal to, it will be greater than, because the hypotheses null and alternative should never overlap. Yeah, and so that's your null, that's your alternative, and that's because she believes that the mean lifetime is greater than 18. Now, if you like, you can put greater than or equal to here on 19.2, but I've always advised students, if it's a one-tailed, to have that sign exactly the same way around as that one, because that will always be the case. Okay, now at this point we can just do this on our calculator. Yeah, so I'm just going to key it in, menu, standard deviation, go to normal CD. I'm going to put the lower bound as 19.2, the upper bound as like 2000 or whatever, as long as it's nice and big. Do standard deviation as 4 divided by root 20, which I just type into the display. Mean is 18. Okay, and I get 0.08986, essentially. And what matters is that it's bigger than 5%. Now, if it's larger than the significance level, you reject. Now let's get this the right way round, because often students get really confused about this. If this is larger than 5%, then this means that the null hypothesis is quite likely. Yeah, it's if it's smaller than 5%, then it means that the null hypothesis is unlikely. Yeah, this figure, which is called a p-value, if they ever ask for a p-value in your hypothesis test, this is your p-value. This p-value is a measure of how likely the null is to be true. And the 5% sig level is basically how strict we're being, if you like. So the lower this is, the more strict you're being. Yeah. Now, we've got higher than 5%, therefore we're going to accept H0, reject H1. Well, we'll just put accept H0. Sufficient evidence to suggest, well, insufficient evidence suggests that the mean has increased. insufficient evidence. You can say it either way round. To suggest that the mean battery life, well, mean length, mean number of, how do I put it, mean number of hours of battery life has increased. And you must put that waffly bit on at the end. I don't like doing it either, but I like getting the marks, so I'm putting it down. Okay, and that's all you need to do. That's a full hypothesis test. And actually, I would say that that is a very typical, very straightforward normal distribution hypothesis test. And you definitely want to get yourself in a position before you take the stats exam of being able to do one as nice and straightforward as that, because it is straightforward. There are worse ones than that. It's, you know, two-tailed one's always worse. When you've got to find a critical region, it's worse. That is not a bad one. Okay, but the B and C, parts B and C are hard in that question, no doubt about it. Okay, hope you enjoyed that video. I'll be doing 2019 next. Keep up the hard work.